Hello. In this lecture, we are going to study the stability of a control system. Stability is defined as the state of equilibrium a system's output attains after being disturbed. For design of a control system, it is very necessary that the stability conditions need to be satisfied. Then only the performance of a system can be governed. Let us consider a linear system which is subjected to a reference input. The reference input is denoted by R of S. This system is also having certain disturbance which is denoted by D of S, and the system is producing the output signal which is equal to C of S. The transfer function for such a system is given as the ratio of the Laplace transform of the output signal to the Laplace transform of the input signal. System's output is dependent on system input, system parameters, and the initial conditions of the system. As disturbance is of unknown magnitude and is unpredictable, any change in disturbance changes the storage of energy within the system. A small change in the system's input, system parameters, or initial condition should result in the small change in the output as well. Then only the system is said to be stable. For instance, if any small change at the input is given by delta of R results in the small change at the output C, then only the system will be said to be stable. If a small change in the input of the system leads to a large change at the output, then the system is driven towards instability and the system is said to be unstable. A linear time invariant system is stable for the following two cases. First one is the BiBo stability. BiBo stands for bounded input, bounded output. If a bounded input produces a bounded output, then the system is said to be stable. For instance, if the input to the system is the unit step and it produces the output in this manner which is bounded, then the system is said to be bounded input, bounded output. We can say with the help of this figure that during the initial part of the input, the output response is transient in nature, and at particular time t, the output settles down and attains a steady value, steady state. Then the output is also said to be bounded. Such type of stability is known as bounded input, bounded output stability. And the second one is the zero input stability. When no input is applied, the output should be equal to zero, irrespective of the initial conditions. This represents the state of equilibrium of the system. This condition is known as asymptotic stability. Let us consider a closed loop transfer function. Let us consider a closed loop control system with unity feedback. The closed loop transfer function for such a system is given by C of S over Rs, which is equal to G of S over 1 plus Gs. This is called as the closed loop transfer function. The characteristic equation for such a system is given by 1 plus Gs is equal to 0. The roots of the characteristic equation dictates the stability of the system. Roots are nothing but the poles of the closed loop control system. Here a question may arise that why zeros do not contribute to the stability? The answer is that because zeros simply changes the magnitude of the system's response. Now we will be discussing different types of systems. The first case is the stable system. The stable system follows the bounded input, bounded output stability. For such a system, the roots of the characteristic equation lies on the left hand side of the S. Here we can see that this is the real axis, the positive real axis. This is the negative side of the real axis. This is the positive imaginary axis, and this one is the negative of the imaginary axis. For a system to be stable, the poles of the characteristic equation should lie at the left hand side of the S plane. If in this region anywhere the poles lie, let it be here or let it be here, the system will be considered as a stable system. The second case is the unstable system. For an unstable system, a bounded input produces an unbounded output. For this type of system, the location of the poles are on the right hand side of the S plane. If the poles lies anywhere on the right hand side, then the system is said to be unstable system. The third case is the critically or marginally stable system. For such a system, the output is neither bounded nor unbounded. In simple terms, we can say that the output response is neither zero nor infinity. The output oscillates in between the finite ranges. The magnitude of such the oscillations are sustained, and the roots of the characteristic equation lies exactly on the imaginary axis. So here the roots of the characteristic equation will be lying. Case 4 is the concept of relative stability. Relative stability is the quantitative measure of how fast the transients decay in the system and settles down, and it is used in relation to comparative analysis of the stability. So let us consider two systems. Let this be system A, in which the poles are located near the imaginary axis, and this be system B, in which the poles are located far from the imaginary axis. As we know very well that if the roots of the characteristic equation means the poles lie on the right hand of the S plane, then the system is said to be unstable, and the necessary condition for stability is that the roots should lie on the left half of the plane of the S plane. Then the system will be said to be stable. As system A is having the location of poles closer to the imaginary axis, so the response will not tend to zero easily, and they will have larger decay time, which means the time taken by the response to settle down to zero will be higher, and the system will be less stable. Whereas in system B, as the poles are located far from the imaginary axis, the decay time will be less, and which will in turn have lower settling times, making the stable system. So the conclusion which can be drawn from this is that as the roots of the characteristic equation or the pair of roots move far away from the imaginary axis, the relative stability of the system improves. Next is the case of absolute stability. Absolute stability is used in relation to the qualitative analysis of stability. Under this condition, if the roots of the characteristic equation, if the poles of the characteristic equation lie on the right hand of the S-plane, then the system is said to be absolutely unstable. And if the poles lie on the left hand of the S-plane, then the system is considered to be absolutable. Thank you.